Okay, good morning. Welcome, and thank you for joining me for this first breakout session of Graph Connect 2018. I'm going to be talking about ingesting data into Neo4j, and I'm going to focus on the use case of master data management, but really it's a general purpose problem. I'm Patterson. I'm a technical director at StreamSets, where I help companies to unlock the value of big data, specifically by figuring out how they're going to move their data around. You can email me, pat@streamsets.com, or you can follow me at Twitter at Metadaddy. So I'm going to start by just talking for a couple of minutes about what master data management actually is, just set a little bit of context. And I'm going to focus on a specific use case in product support. Okay, we want to analyze customer support tickets and join data from different sources. And I'm going to be looking at how we can use an open source tool, StreamSets Data Collector, to move data into Neo4j for this purpose. And what I'm actually going to focus on are the techniques that we can use. So the cipher statements we can use to move data and to build relationships as we unify data from different sources. And I'm going to show you how we can also use cipher to start joining that data once it's in Neo4j and deriving insights that are impossible when it's all spread out. And I'll be showing you this mostly. Where I'll try and get through the slides so that we can get on to the actual practical example. So just a minute or two on StreamSets, the company. We were founded just over 4 years ago, and our founders had worked at Informatica and Cloudera. So they had long experience in data integration and big data. And what they had realized is that the then current tools for data integration, so ETL, extract, transform, load tools, did not address the worlds of continuous streaming, big data, and NoSQL. They're very oriented towards a static schema, relational database world. So fast forward to today, we have dozens of customers, about half from this global 8,000, half smaller companies. Our open source product, StreamSets Data Collector, been downloaded. This is actually a little bit old, this slide. Probably over 2,000 different companies have downloaded Data Collector, and we've seen over 1 million downloads over the years from across the world. One thing that sets us apart is our broad connectivity. So we can connect to over 50 different data stores, streaming systems, and so on. And the innovation in our engineering team goes right back to essentially the dawn of Hadoop. We have committers to Hadoop Core and related projects, so Spark, Scoop, and Flume on staff. So, master data management. So the core problem is that in any enterprise, data is spread out around a number of systems. And this is necessarily the case. We have different applications with different data stores that we use for different purposes. And they can be located on premises or increasingly now in the cloud. And data sets often overlap. Now, this is a good thing in that we want to be able to build correlations between data in different places. We want common identifiers to use as keys between one system and another. But too much overlap gives us pain because we don't always know what the source of truth is for a given piece of data when it's duplicated across data stores. And so it's hard to draw insights from data when it's scattered across different systems. It's hard to build those relationships from, say, an HR system to a support ticket system to records of faults coming in from our IoT platform. So master data management is this whole practice of building a single point of reference from which insights can be drawn. And this is kind of an abstract statement, and it can take many forms. We can build systems that effectively proxy requests out to different data stores, or we can synchronize data into a single location. And that's the approach I'm going to focus on, because that's what we can use with Neo4j. So traditionally, when we did master data management, we would copy data into a relational database. Okay, that was the tool of choice. As Emil was saying on stage earlier on, back in the 90s, you had about 4 choices for database, and they all basically followed the same model. It was just a different sticker on the box of floppy disks. But what if you could use Neo4j or another graph database, if there are there other graph databases? I suppose there must be, to model this master data as graphs. So we can follow those relationships and perform analyses that are not possible, or at least very difficult and time-consuming, in traditional relational data stores. Now, often the biggest problem is just getting the data into Neo4j. Okay, in the room here, how many people have written Cypher queries? Okay, so once the data's in Neo4j, we know what to do with it, right? We can find shortest paths, we can find relationships, we can write queries. It's all golden. But getting the data there is often the single first step that's the hardest. So, my use case that I built a system around. I have a customer service platform that holds support ticket status. So it's got status, priority, the date the ticket was opened, the subject of the ticket, all of that data. And it's got the assignment to support engineers. Now, customer service platform often allows more than just the support engineers to log in and view the ticket. It's going to allow their managers to view that status. And it's going to hold some information about which engineer reports to which manager. But it's not the authoritative source for that data. The HR system, which in my example is an on-premise relational database, is the source of truth for the reporting hierarchy. So if there's any discrepancy between the SaaS customer service platform and the HR system wins. And to help in our fault diagnosis, we have device data that's being reported, might be being reported from an IoT platform. And these are just flat files. So a simple structure, files arrive on a disk that report device status and faults. So the question is, how can we bring these together to get a holistic view so that we can run queries that run right from the faults that devices are experiencing through the support tickets to the reporting hierarchy. Now, StreamSets, this is our kitchen sink slide that shows everything we do. StreamSets is a platform for data ops, so operationalizing the flow of data around enterprises. And it's vastly flexible. As I mentioned, there's about 50 different systems or types of systems we can connect to. I'm not going to go into detail walking around this slide. Suffice it to say, we can talk to APIs, IoT platforms. People use us for reading firewall, web server logs, databases, and then we typically feed big data stores. So we partner with Cloudera and MapR, Databricks, and we can write data into Hadoop, Amazon S3, Google Cloud, and so on. And what we're really enabling is analytics. Okay, we're reading typically from operational data stores, writing into more analytical big data stores for the purpose of drawing those insights. And this is all really complex, and it can be on-premise and in the cloud, but really it boils down to we think of ourselves as a Swiss Army knife for data. We can build data pipelines that source data from any of dozens of possible sources, transform it, and write it to a similar number of destinations. So, about 18 months ago, one of our SEs came to me and said, one of our customers, financial institution, is really interested in writing data into Neo4j for analysis. Can we make that work? And I went away and looked at Neo4j and started to bolt some pieces together and found out that it was actually pretty straightforward to work with Neo4j from standard tools. And so this is your first, just as a quick point of interest, how many people in the room have heard of StreamSets before today? Okay, a good smattering. How many people have used StreamSets before today? Well, one or two. Okay, great. So this is a pipeline that we'll actually go into more detail in a little while. But it's reading data from a delimited file from disk, performing, let's see, about 4 different transformations, including filtering relevant data, and then writing that data to Neo4j. And what I discovered is that the Neo4j JDBC driver is really high quality and really performant for these purposes. And we can construct cipher statements. So I guess technically they're not queries because we're creating nodes. But we can create nodes through cipher and create both nodes and relationships very efficiently. So you can see here I'm creating a node for a fault and matching a device and then creating a relationship between where a fault affects a device. So how many people in the room have used this JDBC connector? A handful. Okay, oh, more than a handful. Right, so this is not part of Neo4j product per se, and my machine has just gone to sleep, so I'll need to wake it up later. The JDBC connector is a contribution to the broader Neo4j project by an Italian company called Laris BA. But it is the official JDBC driver for Neo4j. When you go and look on the JDBC website, this is where it takes you. Now, it's actually very high quality. I've worked with a lot of JDBC drivers. Quality is very, very variable in the way that they implement the JDBC interfaces. There are often unimplemented methods that just throw an exception instead of doing something sensible. But I haven't had any problems with this driver. It works very nicely indeed. One technical note, it can use Bolt or HTTP/HTTPS. Now, Bolt is a binary over TCP protocol that the Neo4j drivers use to communicate with the server. So across all the languages, they all use this low-level protocol. And if you're making choices when you use this JDBC driver, Bolt sends about 1/10 of the number of bytes over the wire than JSON over HTTP. So definitely, unless you have an overriding need to use HTTP, I would use Bolt when communicating between the JDBC driver and the server. And happily, it's enabled in Neo4j by default because it's the main method of integration. And when you set up JDBC, you'll need a URL of this form. So JDBC:, so Neo4j selects that driver, and then the Bolt selects that protocol, and then the host name. So the architecture I built is very, very simple. I'm going to read MySQL in one pipeline, and I'm going to read support tickets from Salesforce. So full disclosure, before StreamSets, I was a developer evangelist at Salesforce, so I know their system, I know their APIs. I'm going to read support tickets from Salesforce Service Cloud. You could equally apply this to Zendesk or any other support ticket system. So I'm going to read those in a second pipeline, and then I'm going to read those flat files and do some transformations in the third pipeline, but bring them all together, unify them in Neo4j. And this is the goal here, is to create a graph where the purple nodes here are employee data. So if you were to kind of pull on the right place in the graph, you would see it settle out into a reporting hierarchy. That's coming from our employee database, our HR system. The green nodes are support tickets. They're coming from Salesforce. And then the red nodes are devices, and they really connect the tickets to the blue ones, which are the device faults that are coming from our IoT system. So what I'll do is I will just log back into my laptop, and then we can go to the eye candy. And unfortunately, when I do the eye candy, my eyes need some help. OK, so this is StreamSets Data Collector. As I mentioned, it's Apache 2 licensed, open source. It's the, I guess, the core of our platform. And I have my 3 pipelines here. So if we go look at employees, it's a very, very simple pipeline. What I'm going to do is I'm going to read data from MySQL. So really, this is just a microcosm of an HR system. We've got an employee table and a table of titles. So our employee table just has a few fields, but crucially, it has the reporting structure. Every employee, apart from our VP, has a manager ID that links it to another employee. And we're in this kind of relational, denormalized world, or normalized world, rather, where instead of having job titles in the employee table, we have a foreign key to a title table. So like I say, this is 2 tables where real HR systems probably have dozens, but it's enough to show the core of what we're doing. So over in StreamSets, we can read this with a JDBC data origin. So what we can do is we can actually have the database do some of the heavy lifting here. So this is just the standard SQL query that is going to read fields from that employee table, join it to the title table, because we don't want numbers in Neo4j for job titles. We want the actual strings. It's going to do that join in the query, and then just write that data to Neo4j. So this is where the magic starts to happen. So we have our JDBC connection string, and then we have some Cypher. Now, what we're doing here, what's going on in this pipeline, is that we kind of have a micro-batch architecture. It's kind of similar to Apache Spark. We read batches of data from JDBC, so it might be 1,000 records at a time, feed them through this pipeline. So each batch gets fed through here. And then this Cypher is executed for each record. Okay, we're reading records from JDBC and then writing them, well, to JDBC, to Neo4j. And we get to write freeform queries. Now, by default, we would use a different JDBC destination that is designed for relational systems, where we're going to do SQL inserts. Okay, you wouldn't need to write a SQL insert. You would just kind of say, OK, these are the fields that I'm interested in writing, and the system builds the insert for you. Because we're working with Neo4j, we do Cypher, and we get to write a freeform query here. It kind of says SQL query, but it's what we submit to JDBC. And we substitute in values from the record that we read. So we can set an employee ID, the name there, the job title. And then, crucially, we're using a merge, because what we're saying is, this is not a one-time process. We're going to need to periodically read this employee database and then update Neo4j. So the first time round, we're going to want to create nodes from then on, we're going to want to merge nodes based on this employee ID because employees might be changing their names. They certainly might be changing their manager ID, moving around the company. And then we create the relationship between the employee and their manager. And this is pretty straightforward. We're saying matching the manager where the IDs correlate and creating that relationship. And then another interesting trick is that we can delete outdated relationships all in the same statement. Because what we say here is, with that same employee that we're working with, if there is their former manager, so if there's already a relationship in Neo4j, that's this thing here, where the employee, the manager's ID is not the employee's manager ID, then delete that relationship. So this is a really neat technique, and it's not specific to data collector at all. It works with any way of ingesting. If you wrote your own app to ingest data into Neo4j, this housekeeping of the graph as you read it in using merge and delete. Okay, one more detail. Usually this would run continuously. I wanted to kind of show a batch use case here. So I'm saying that when there's no more data, we want to stop the pipeline. So this is just going to run, read my employees in, and then stop. And just double check here. This thing that always kills me is, okay, we have an empty database. So if the demo gods are smiling on us, this should flick up. Yeah, so it flicked up. It was almost imperceptible because it's like ridiculously small database. But we read 17 records. We wrote 19. 2 of those are events that went to that, the finisher thing. And over here, we should be able to see, click in the right place, our lovely graph. And you know, we can look at this, and you know, this is a fairly basic graph, but we can start to run Cypher queries. So clearly, we can run queries that kind of match what we could do in any relational database. So we could say, which manager has the most reports? We can eyeball this because it's so small. It should be Kim Park, but when we run it, yeah, it's Kim Park, and she has 4 reports. Can I zoom in on this? No. So that's just mapping what you can do in relational terms. But we can start to run queries that are very difficult or impossible in a relational system. So we can do shortest path. So we have Michael Sinclair and Peter Preston, who are down here. They should be in different parts of the organization. Michael's over there. Peter is over here. Apologize for people at the back. Can I zoom in here? Oh, yeah. Ah, there we go. That's much better. Okay, so we can run that and see that, you know, if we follow reporting relationships, Michael and Peter are far separated in the database. And this is one of those queries where it's one line of Cypher, but you'd have to start writing loops and jumping through all kind of hoops in a relational database. And then by contrast, if we just run another quick one with Tony and Peter here, we should be able to see that they report to the same manager. Now, this is all very interesting. What happens when we move somebody around? So let's move Peter to report to a different line manager. So if we go over here to MySQL, update that. So what I'm going to do here is say, okay, we have this job runs periodically, this pipeline. If we run it again, that Cypher runs, and what's happened is that it's updated Peter's node, and it's removed the old link. So if we go back to Neo4j and take a look at the graph, it's pretty hard to see here, but we should see there, Peter's now reporting to Hannah, who now has 3 reports, and the results of our 2 queries should be completely different. So now Peter's actually in the same org as Michael, and he is across the company from Tony. So we are maintaining the state of Neo4j continuously. We could run this we can run this batch job as often as we liked. But batch jobs are not very interesting. You know, the word stream in the StreamSets name kind of implies that we're really thinking about continuously streaming data. So here we have reading Salesforce cases. So here's Salesforce. I've got about 8 support cases open, and they all have priorities. Let's go in on this a bit. They all have priorities and case owners and so on. And what we're doing here is, again, a very simple pipeline. We're running a query to pull these from Salesforce. So here's the interesting data. And again, writing to Neo4j using very similar pattern. Merge, creating nodes, relationships, and deleted, outdated relationships. But this one's a little bit more interesting in that I can, just let me reset this, make sure that I get all the data. I can run the pipeline. It'll pull those first 8 records. And what it's done is it's knitted the data together. So if I look at the graph, so I'm correlating the data here. Alex is working on 3 support cases here. Support cases are green, devices are red. And again, I can run Cypher queries. So I can do a simple one like, okay, what's the support engineer with the most cases? And that's Alex, as we saw, he has 3. And then, again, I can join data that's in different places. So I can say, okay, who's the director with the most high priority cases? And it's going to be Andrew Smith. So my Cypher query there is joining data that's in HR, this reporting structure, following an arbitrary number of reporting links to find a person with a job title that owns these high priority cases. This might be important to see if one department is becoming overloaded with high priority cases. Now, what's really neat here is I've moved 8 records across, and if I start playing around with these, maybe I want to change a whole bunch of these to high priority just to make the numbers different. What I should see, whoops, save those. What I should see when I go back here is that now 11 records have been moved. What's actually happening is that this Salesforce origin is subscribed for updates on changes to cases. So there's a protocol to get notifications when anything changes in Salesforce in real time. These are push notifications, and push them to Neo4j. So now I'm creating new nodes, modifying new nodes, rewriting those links dynamically. And what should happen here is that if I go back into the graph, suddenly the hierarchy isn't very different, but those number of high priority cases should change. So now Sanjay has the most high priority cases. So data is changing dynamically in the real world. Those changes are being picked up by a data pipeline and being written into Neo4j. So now we're not just running our analytics on a static data set. We're running on live changing data that is literally changing from 1 second to the next. Okay, so the last little bit of integration here is our device faults. So here, I've got to transform the data a little bit because my faults are in these pretty obscure CSV files. I've got serial numbers, timestamps, and fault codes. Most of it is chaff. All of these zeros are just status reports. They're not interesting. It's anything with a non-zero status that is some kind of warning or something. And so what I'm going to need to do here is read the delimited file, parse that CSV file, rename a field, that SN I want to rename to serial number, convert the data types of fields. So everything comes as strings from CSV, so I'm making date, times, and integers. And then I'm going to filter out on a condition. So I only want records whose fault code is greater than 0. And then I'm going to do a lookup, because I don't want numerals in Neo4j. They're not very useful for my analysis. I want actual strings representing the faults. And then I'm going to write all that into Neo4j, and it's very similar cipher to before. Now, one really nice thing I can do here is have a quick look at the data as it's going through. So I can see the kind of data that gets read from the disk. I can see how fields are renamed, data types are converted, and I can see how most of this data goes to the default discard, but this record here is going to go through the lookup and be assigned an actual fault string. So this gives me some confidence that my pipeline is going to do the right thing when I run it. So what's going on here? I've got 86,000 rows, and you'll see there they were ingested in about less than 2 seconds. So that JDBC driver is very efficient. I was running 86,000 of those cipher statements in just a couple of seconds. And over here, the graph goes a bit nuts because I've got 800 or so 800 or so nodes I just created, and we only get 300 here, so it's always a bit of a lottery. But we see here now that these devices are surrounded by these faults. And it lets me, again, write cipher that spans the different systems. So I can say, OK, which support engineers are handling critical faults? You know, make sure that these important support cases are assigned to the right people. And again, this was not apparent from any single source system. Okay, device serial number was in Salesforce, and the fault codes are coming from IoT. So here I can see, okay, 3 employees are handling critical faults, and Alex is handling 2, and the other ones are handling 1. So I can make sure, okay, Alex is a hotshot support engineer. He can handle those critical faults. And I can do other things like report on devices which have faults but don't have a support case open for them. So this could be crucial information. So I've got 2 devices there that have reported faults, but nobody's opened a ticket. And now I can kind of simulate more data arriving. Just drop another CSV file into the directory. And this thing should spin up just in a couple of seconds. So it's spun up from 86,000 to 172,000. And again, it's knitting all of this data together, building those relationships. So now if I go to Neo4j and say, OK, I've got another day's data that's come in. Now I've got, now I've got 3 devices now that have faults but no support tickets. So this is really giving us the power to draw these insights from the systems around the enterprise. OK, if we can go back to the slides. So just writing data into Neo4j is not the only use case that this tool can be used for, data collector and the StreamSets data ops platform. We do a lot of work, what's called data lake replatforming, so building data lakes in Hadoop. As I mentioned, we partner with Cloudera and MapR with their big data products. The world of IoT, there's a lot of data to be read in from devices and IoT platforms, bringing data together for cybersecurity use cases. So parsing those log files from firewalls and web servers and other equipment, and working with continuous streams of real-time data. We integrate with Kafka and other message systems. The marketing slide. So we have some great customers. GlaxoSmithKline, the major pharmaceutical, actually uses us to bring data together from all of their drug discovery systems, all the drug trial data into a single data lake so that their scientists can make more effective use of that data in one place. Cox Automotive build a group-wide data lake from data from all of their subsidiary companies. And Availity in the healthcare space found that StreamSets was able to accelerate their time to move data between different systems. So coming to a conclusion, we might even have a couple of minutes for questions. Neo4j can provide insights into data that are just not available when the data is in rows and columns and spread across silos. This shouldn't be news to anybody here. It's one of the main points of value here. We can run these graph queries that are just not feasible in relational databases. That JDBC driver is an excellent tool for bringing together standard applications that use this JDBC interface with Neo4j. I didn't look at the reading side, but you can write Cypher queries that bring back data that looks like a JDBC row set just as easily as writing data. And Data Collector from StreamSets can read data from a huge variety of streaming, flat file, relational database sources, and work with Neo4j very handily via that JDBC driver. So there's some references here. They'll be in the slides that are available to you elsewhere. And with that, I think I have about 2 or 3 minutes for questions. Yeah.
Can you differentiate the StreamSets pipeline from like an Informatica cloud pipeline or a ID pipeline?
Yeah, so the question was, can I differentiate StreamSets data collector, I guess, from Informatica? I'm not an expert on Informatica. My understanding is that they're a bit more focused towards the relational schema-driven approach. We tend to work more in a schema-on-read kind of way. So when I read that data from the relational database, I don't have to set up schema. I can introspect the data in the pipeline using the data collector like an IDE to see what's there and start building my rules to switch the data around. So if I add some columns to the database and run the pipeline again, it really doesn't care. They'll come through the pipeline and be written out to the destination. So we call it an intent-driven approach. Yeah, I think that gentleman there was the first hand I saw. Go on.
When you're changing data sets from the source, how does it update the graph? Does it delete the old relationship and set it anew, or does it create the entire graph over?
So good question. When I update the graph, what am I doing? Am I deleting and creating or creating the whole graph over? What I'm doing is I'm using a Cypher merge to find a node with a particular ID and overwrite its attributes, okay? Because my manager ID might have changed. And then I'm creating the relationships between employees and managers, for instance. And then what I'm doing is I'm doing a match to find a relationship where the condition is no longer true. So if I've now got an outdated relationship where the employee's manager ID is not as the same as that manager ID, I delete it automatically. So I'm kind of like housekeeping the graph. It's pretty efficient because I'm doing the least possible amount of work. I'm not deleting and then recreating the graph. That would be pretty disastrous. I'd lose all my relationships because these things can all be updating kind of asynchronously. So question that gentleman there. No, I don't have any quantitative feel there. I mean, you could see there I was bringing in, 86,000 records in less than 2 seconds. So, that's just kind of hand wavy. It works, and it works well on, everything's running on my laptop. Yeah, I need to look into the admin tool. Cypher's the only tool I've used there. Okay, I'm getting the wrap-up signal from the back. So with that, I'd like to thank you all very much for coming. And enjoy the rest of the conference.